Hello friends, in this video I'd like to solve the following problem from a Bangladesh Mathematical Olympiad, higher level 2023, problem number 10. So it is meant for students of higher classes of high school in Bangladesh, if I am not mistaken. Viewers from Bangladesh may correct me if I'm wrong. Let P be a monic polynomial of degree 2023 with real coefficients such that P of 0 plus P of 1 equals 0. And moreover, let R1, R2, and so on, up to R 2023, these numbers are between 0 and 1, let them be, not necessarily distinct, real roots of P. We wish to find the maximum of the product of all the roots. So we are considering the maximum of roots, product of roots, of polynomials which satisfy our constraints. It's a very nice problem. Here are my hints. Everything hinges on the following lemma, which I will prove. I will prove for the sake of completeness. Let a1, a2, and so on, an be positive numbers whose product is 1. Then we have the following inequality: 1 plus a1, 1 plus a2, and so on, times 1 plus an. This is always greater than or equal to the power of n. And equality is attained if and only if all of them are 1s. I will prove it in a minute. And assuming you may try to prove it yourself. And hints, further hints. Generalize this problem to any odd number of roots. Not 2023, but put n, because n is faster to write than 2023. We may, of course, assume that all the roots are 0, because we are taking the maximum of the product. If one of them is 0, then the product is 0 as well. You should show the following equality: 1 minus r1 over r1, 1 minus r2 over r2, and so on. Product of these fractions is 1. Let ak be 1 or minus rk over rk, and express our roots in terms of these ak's. And finally, use the lemma. Everything hinges on the lemma. So give this problem a try, and I will see you in just a minute. Right. So let's start with the proof of my lemma. Proof. To prove it, I will not use derivatives, but I will consider this function. So let f of a1, a2, and so on. I define my function to be 1 plus a1, 1 plus a2, and so on, 1 plus an, where a1, a2, and so on are positive, and their product is 1. Let me minimize my function. First, notice the following. First, f is obviously continuous. So I wish to say that it attains its minimum somewhere, but to say that it actually attains its minimum, I will look what happens when we are getting closer and closer to the boundary of this set described by these conditions. Notice that also we will assume that n is greater than or equal to, because for n equals 1 this is trivial, there is nothing to demonstrate. And notice the following, that if, maybe I will write it in different color, if, for example, if ak, one of the variables, gets closer to 0, then some other variable must be getting closer and closer to infinity. How do I know it? Well, because of this constraint. If one of the variables becomes smaller and smaller, for the product to be 1, other variable must go to infinity. Likewise, if one of the variables go to plus infinity, then some other variable must go to 0. Yes. So maybe let's be specific. Then AL goes to there for some L. All right. And what happens if one of our variables go to infinity? Well, notice that 1 plus A1, 1 plus A2, 1 plus AN, it goes to infinity if one of the variables goes to infinity. Pretty easy to see, because, well, everything is between 0 and plus infinity, so each of these fractions, each of these parentheses is greater than 1, and if one of them goes to infinity, the whole product goes to infinity, which means that f becomes unbounded as we approach the boundary of the set of our domain, basically. When we approach the boundary of A1, A2, and so on, where A1 and so on are greater than 0 and their product is 1. Which means that our function, which is continuous, attains its minimum somewhere in the region, not on the boundary, yes? Because on the boundary, actually, the maximum is attained. So f attains its minimum for some A1, A2, and so on, AN, lying in our domain. Maybe let's call this set D, or some element of this set D. Not on the boundary, it's the key observation. Alright, and now what I will show is that actually each of these coordinates must be the same. We will show that if f attains its minimum at point A1, A2, and so on, then all of these coordinates must be actually the same. And I will prove it by reasoning to the contrary. Suppose to the contrary, that, for example, that AK is not equal AL. Alright, and now, where, let's say, K is less than L. And now, key observation is to replace these two variables by their geometric mean. So replace AK and AL by their geometric mean. What happens? Well, let's take a look. Let's compare, because notice that if I plug in two geometric means, the product stays the same. Then the product of A's stays the same, it's still 1. And what happens to the value of our function? Well, let's take a look. Actually, I claim the following, that our value of our function decreases. Oh, I have this AL, AN. I actually claim that this is strictly greater than A1. Here we have our mean. Here we have our mean again. And here we have our last variable. Well, notice that this is equivalent to saying the following. 1 plus a1, 1 plus ak, 1 plus al, 1 plus an is greater than 1 plus a1, 1 plus square root of ak al, 1 plus ak al, 1 plus a. Everything stays the same apart from these terms right here. So this inequality is equivalent to saying that 1 plus ak, 1 plus al is greater than 1 plus square root of ak al squared. Notice that we have 1 plus ak plus al plus ak al greater than 1 plus 2 square root of ak al plus ak al, and this is equivalent to saying that ak minus 2 times square root of ak al plus al is greater than 0, and this is in turn equivalent to saying that square root of al minus square root of ak squared is greater than 0, and this is true because we are assuming that these two numbers are the same. So we have already demonstrated that this is the case. So we have actually decreased the value of our function, which is impossible because we assume that our function attains its minimum at these coordinates. So we have some kind of contradiction. We have contradiction because our function was assumed to attain its minimum. All right, so we have demonstrated that our function f attains its minimum only at what point? Well, each coordinate should be the same, so it should be 1, 1, and so on. 1. This minimum is what? This minimum is f of 1, 1, and so on, 1, and this is 2 times 2 and times 2 to the power of n, which closes the proof of my lemma. This entire part was showing the validity of my lemma. Now, for the actual problem. You will, by the way, this lemma appears to be very useful, not only in this problem, but in other types of problems. So I suggest that you remember this result. All right, so let's go back to our original problem. So we are considering monic polynomials. Monic means that it has the leading coefficient of 1. So let p of x be written as x minus first root, x minus the second root, x minus the third root, x minus the nth root. And as I suggested, I will generalize the problem from 2023 to any odd number, where n is any odd integer, any odd positive integer. All right, so we assume furthermore that these roots are between 0 and 1. We assume further that p of 0 plus p of 1 equals 0. And we wish to do what? To maximize the product of all the roots. How can we maximize this? Well, let's take a look. Let's take this expression. Or maybe notice first that since we wish to maximize this product R1, R2, Rn, we may safely assume that, well, that our roots are greater than 0. Because if one of them is 0, then we have product equals 0. Alright, now I will use this condition. What is p of 0? If we go back to our definition, p of 0 is minus r1 minus r2 and so on minus rn plus what exactly? 1 minus r1, 1 minus r2 and so on, 1 minus rn, and this should be equal 0. And now it's necessary, now it's important to see that this is minus the product because the number of our roots is supposed to be odd. So here we have minus r1, r2, rn plus 1 minus r1, 1 minus r2, 1 minus rn equals 0, which means we can put this on the right hand side, we can do division, and we will get the following result. 1 minus r1 over r1 times 1 minus r2 over r2 times, and so on, 1 minus rn over rn equals 1. Now I will make a small substitution. So let ak be equal 1 minus rk over rk for k between 1 and n. Alright, now let's express rk in terms of ak. Notice that since ak equals 1 minus rk over rk, this is the same as 1 over rk minus 1, which means that rk can be written as 1 over 1 plus ak, which means that r1, r2, rn is 1 over a1, 1 plus a2, 1 plus an. It should ring the bell, because here we have something which appeared in our lemma. Moreover, notice that after our substitution, we have a1, where to put it? Maybe I will put it right. By our substitution, a1, a2, and so on, an, these numbers are, their product is 1, and they are positive. They are positive because our roots are assumed to be between 0 and 1. Alright. The only possible problem is when one of the r's is 1, but this cannot happen, because if one of our roots is 1, then for this equality to be true, some other must be equal 0, but we have excluded this possibility. So notice that r1, r2 times rn attains its maximum exactly when 1 plus a1, 1 plus a2, and so on, 1 plus an attains its minimum, because it's in the denominator, and it is positive. Attains its minimum. And by our lemma, 1 plus a1 times 1 plus a2 and so on, 1 plus an, attains its minimum only at a1 equal a2 equal and so on equal an equal 1, and this minimum is what? Is 2 to the power of n. It's 2 to the power of n. Alright, but a1, a2 and so on equals 1. What does it say about rk? Well, remember that rk is 1 over 1 plus ak, and it's 1/2 if ak equals 1, which means that we have our answer. The minimum, or the maximum rather, the maximum of r1, r2, rn equals 1 over 2 to the power of n. Remember that our expression is in the denominator, so it's 1 over 2 to the power of n, and it is attained only for polynomial with all the roots the same. P of x equals x minus 1/2 to the power of n. And this closes our solution. This is our actual answer to our problem. Very nice problem, I'd say. Horrible ellipsis. Oh no, oh no. Why? Whatever. Thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.